So I'd like to take the opportunity now to apply Newton's second law to the solution of problems involving uniform circular motion. Now I understand completely that the acceleration of circular motion is v squared over r, and that forces cause that acceleration. Such forces I call centripetal forces, forces that seek the center, or indeed centrifugal forces that are directed away from them. So now that I understand the basic technique, there are some classic problems that need to be reviewed. So I'd like to go over them now. So 3 or 4 problems that are worth knowing. Many of us have had the experience to go to an amusement park, perhaps down the shore or at a local fair, where there's a ride that's typically referred to as the Gravitron. It's a large cylindrical room, and the participants go inside and stand against the wall. The entire room then is rotated. At first it starts out slowly because there's some motors that create what we call an angular acceleration, increasing the speed, increasing the speed, increasing the speed. But eventually you reach a certain critical speed at which the riders of the ride are stuck to the wall. In the modern version of the ride, very often when you lean against the wall, you're leaning against a sort of board on wheels. When the ride starts going fast enough, you roll up the wall a bit and you find yourself suspended, no longer in contact with the floor, but stuck to the wall. Because that's not an everyday occurrence, we find it quite amusing. In my day, you would go in and the wall would be completely vertical and you stood on it, and when it rotated around, the floor would actually drop out. The sense of danger was significant because you look down and the floor is way down below you now and you're stuck to the wall. And you look to your left and to your right, you see the other folks on the ride are similarly stuck to the wall. And you try to roll this way and that way, experiencing a sensation that's a little different from everyday life. So I'd like to analyze that. I'll begin with a picture of what this ride looks like if you're having trouble visualizing. So I have a large room, cylindrical in shape, like thus, and it's going to rotate about an axis that goes through the center. So in principle, I've constructed this thing. I know the radius of circular motion is a line drawn perpendicular to the axis of rotation, to the wall here. That's going to be the radius of the circular motion. So what you do is you go in and you get up against the wall in the thing, and as it rotates, you find yourself stuck to the wall. No need for a floor. In order to analyze this motion, naturally, I'll draw a Freebody Diagram showing all of the forces that act on the rider. So here's a Freebody Diagram for the rider. They have a weight mg, which is directed downward, and the wall behind them exerts a normal force which is directed radially towards the center of the ride. The normal force is called normal because the word normal means perpendicular. So the force of contact between the rider and the wall of the ride is naturally perpendicular to the wall and coincidentally radially towards the center of circular motion. It is the wall that pushes you around in a circle when you're inside the ride. Were it not for the ride, if we could somehow open up the ride or make the wall vanish, then you would fly in a straight line, actually projectile motion, according to the law of inertia, Newton's first law. So it's the wall that's directing you towards the center of circular motion, and your fear is that you'll fall out of the bottom of the ride. And that fear is not surprising because your weight is acting downward. Your weight is always acting downward. So your brain asks, why do I not fall? If I do not fall, I don't in fact have any vertical acceleration at all. It means there must be some force directed upward that prevents me from falling. What force is that? It's got to be one of the forces that I already know. There are no springs, there are no ropes, thankfully. That would make this extraordinarily dangerous. What is the force directed upward that prevents me from falling out of the bottom of the ride? That's right, the friction force directed upward is a force that opposes the weight and prevents me from sliding down the wall. The faster the ride goes, the larger the normal force has to be. The larger the normal force, the larger the friction force, and ultimately I can create a friction force that is sufficiently large to prevent me from sliding out of the bottom of the ride. This, of course, would be static friction force. So here's my free body diagram showing all the forces that affect the motion of the rider. Now, identify what forces are centripetal. The weight force is directed downward, not towards the center at all. It doesn't even have a component that points towards the center. And the same for the friction force. It points upward, in no way towards the center. The only centripetal force in this problem is the normal force, and so it is the normal force that is equal to mv squared divided by r. It is the normal force that is the centripetal force in this problem. But the normal force is the force between the rider and the wall, and I don't generally know anything about that force. So to continue my investigation in this problem, I want to look at the vertical forces. They are not centripetal forces. But by looking at my free body diagram with the friction force directed upward and the weight directed downward, I can see, particularly from the recent experience I have solving such problems, that the friction force directed upward is equal to the weight force directed downward. But of course, I know something about the nature of friction force. I know that I have an equation that I can use to calculate it. That equation is mu times the normal force. Now don't jump the gun here and say that the normal force is equal to mg, because it's not. The normal force is equal to mv squared over r. The normal force is the centripetal force in this problem. But I can solve this equation here for that normal force. The normal force is equal to mg divided by mu. That's the first time I've seen that expression, but it goes in accordance with Newton's second law applied to this free body diagram. So that's going to turn out to be generally true. The normal force is equal to mg over mu, but in its role as the centripetal force, the normal force is also equal to mv squared over r. So if the normal force is equal to mv squared over r and the normal force is equal to mg over mu, then these are equal to each other. And so I can write the expression that mv squared over r is equal to mg divided by mu. Notice that on the left-hand side and the right-hand side of this equation, the mass appears. So if I divide both sides by the mass, we typically say the masses cancel. And what I'm left with is that the speed squared divided by the radius is equal to g divided by mu, and I can solve for speed. I'm not really solving a particular problem here. And so what I choose to do is just solve for speed and think for a little bit about what my answer says about the nature of the thing. To solve for the speed, I'll multiply multiply r over to the other side of the equation, where it's already divided by mu, so I have gr divided by mu, and to get v, I'll take the square root of both sides. And so I find that the speed, which as it happens, is the critical speed required for the ride to rotate at. Right? So the passengers have to be going around with this tangential speed at a minimum, or they'll fall out of the bottom of the ride. Imagine this, you go in, you stand up against the wall, they don't ride the wall, rotate the wall at all, they don't rotate the room, and they drop the floor out. Well, you fall out. Imagine you go in, you stand against the wall, but they rotate the room very slowly. They drop the floor out, and you fall out. There's a critical speed that the ride must rotate in order for the passengers to stay in. Obviously, from an engineering point of view and from a legal point of view, it's really important that I know what this speed is, so I can make sure that there's some sort of gauge or meter on the ride that tells me that I've reached that special speed in order to operate the ride safely. This application is known as the Gravitron, and it is a classic problem of circular motion. Now, a second problem that I'd like to demonstrate today, and here I have an apparatus for demonstrating it. I have a mass on the end of a string here, and we're familiar with the mass on the end of a string. In fact, it's a really important problem of physics. When I let it swing to and fro like this, it's an apparatus that everyone is familiar with because we refer to this as a pendulum. A pendulum is critical to the history of human technology and scientific advance because, of course, I can use the periodic motion of a pendulum as a clock. It's how I have a sense of time. Pendulum motion is periodic motion, just like circular motion is periodic motion. It's motion that repeats itself. So solving the problem of the pendulum is a really interesting one, but it turns out that it won't be a problem that we solve until more advanced courses in physics. The problem that I'd like to solve now is not this simple version of the pendulum, but actually one that is slightly more complicated. Here I take the mass and I swing it around, allowing it to make a circle as it swings around. I find that there's a certain time period associated with this motion as it goes around. I can't force it to go faster. I can't force it to go slower at this particular angle. If I go faster, the angle gets larger. And if I go slower, then the angle gets smaller. So clearly there's a relationship between the speed and the angle. Observe how the string moves around in a shape that might be described as a cone. This particular problem of physics is known as the conical pendulum. And it's one I'd like to solve now. So I start with a diagram. So I need some kind of a support structure here. So I'll draw what is the ceiling in the problem. So there's the ceiling. And I hang the mass from a string of length L. And here, I guess this is some mass M that I'm hanging here. And as it goes around in circular motion. This is tricky to draw. We'll give it a shot. There's the circle that it goes around. I did a fair job of that. That's the circle that it goes around. And here's a line drawn from the vertical that goes right through the center of the circle. And I can measure and find that the angle between the string and the vertical, I'll call that angle theta. And I would like to analyze the motion of this physical conical pendulum. So obviously, after I've drawn a picture and I understand the motion, I want to draw a free body diagram. So I begin by drawing a square like I do for a free body diagram and acknowledge the fact that the bob at the end of the pendulum has a mass mg, and so I draw that directed downward. However, the only other force acting on the pendulum is a tension force that is directed along the string. Notice that that force is directed at an angle with respect to the y-axis and the x-axis. So naturally what I'll do, like I do anytime I encounter a force at an angle in a Newton's second law problem, is I'll decompose that force into its components. In this case, I want to particularly find components. I'm looking for a component that is centripetal, because I'm trying to explain the circular motion of the bob, and so I'm looking to identify a force that points radially towards the center of circular motion. And as such, I'll draw in two components here, a component of the tension that is centripetal and a component of the tension that is along the positive y-axis there, say a vertical force, not a centripetal force. But I have to work out what those components are by looking at my diagram here. Well, I see the angle theta is the angle between the string and the vertical. If I draw another vertical off the mass here, just a little bit, I can see that the angle theta is alternate interior to this angle here between the tension force and the vertical. Therefore, the vertical component of the tension force is T times the cosine of theta, and the radial component of the tension force is T times the sine of theta. Now I have a free body diagram to which I can apply Newton's second law for rotation. What I'm looking for is any forces that are centripetal or centrifugal. It's certainly possible if the problem's sophisticated enough, there might be forces that point away from the center of circular motion, as there were, for example, when I did the vertical loop problem. However, in this case, T sine theta is the only force that is directed towards the center of circular motion, and therefore, T sine theta is equal to the mass, the speed squared, divided by the radius. But just like in the Gravitron problem, where I didn't know the normal force, I do not know the tension force. So just as I did in the Gravitron problem, I'm going to investigate the vertical forces. I can tell from looking at my free body diagram that the component of the tension directed upward must be equal to the weight directed downward, because the vertical forces in my free body diagram have to be in force equilibrium one with the other so that there's no vertical acceleration. There's only centripetal acceleration in this problem. There is no vertical acceleration. So the T cosine theta force upward has to be equal to the weight force mg downward, and therefore the tension is equal to mg divided by the cosine of theta. Well, I'll make that substitution in, where I have this expression T sine theta is equal to mv squared over r. The T is equal to mg divided by cosine theta, then again multiplied by sine theta. Now you see the very satisfying thing here, where mv squared over r equals mg over cosine theta sine theta, that there's a mass on both the left and the right hand side of the problem, and so once again the mass cancels. This motion does not depend on the mass of the object. This motion does not depend on the mass of the object. That was great for the Gravitron, because if you want to go on the Gravitron ride and take your pet guinea pig with you, it helps that you're going to stick to the wall and the guinea pig is going to stick to the wall because it's mass independent. In the case of this pendulum bob, I don't much care about it one way or the other, whether it's mass independent, but in some cases when the mass goes away, it's helpful. And it gives me an interesting physical result. The sine of theta divided by cosine theta is something special, isn't it? It's the tangent of theta. The sine of theta divided by the cosine of theta is the tangent of theta. So this expression becomes v squared divided by r is equal to g times the tangent of theta. And so solving for the speed of the pendulum, I find, just as I did when I demonstrated it here experimentally, the speed depends on the angle. The angle depends on the speed. gr times the tangent of the angle theta. Notice that once again I have that fundamental bit, the square root of GR, that appears. When I was looking for the critical speed to go through the top of a loop, it was the square root of G times R. When I was looking for the critical speed going over the top of a hill, it was the square root of G times R. When I was looking for the critical speed in the Gravitron problem, it's the square root of G times R divided by mu. I'm seeing the same kind of algebra happening over and over again in my problem solving. Recognizing patterns in your problem solving is a huge advantage to becoming good at solving physics problems. So the speed of the pendulum going around this way is equal to the square root of GR times the tangent of theta. The third problem that I'd like to solve is actually two problem solutions, one of which I've already done before. I've realized that in order for a car to negotiate a curve, it has to execute circular motion. Even if you travel in constant speed in your car, when you go around a curve, you are accelerating. There must be a force that is the cause of the acceleration. And I think we all agreed that the force that makes your car go around in a circle is friction force. Indeed, your steering wheel, when you turn it to and fro, is directing the magnitude and direction of the friction force that is causing the circular motion. When you turn the steering wheel to the left, the friction force is directed to the left. When you turn it greatly to the left, there's a lot of friction force to the left. Similarly, if you turn the steering wheel to the right, the friction force is then directed to the right. So it's friction that makes a car go around in circular motion. This problem is familiar. I'm going to solve it quite rapidly as an intro to the problem that I actually want to solve. Consider here a car on the roadway, which I've complained before I'm not terribly good at drawing because I have to draw the car in such a way that it appears as though the car is coming towards you. So here I see the wheels and the headlights, and so this is the car. It's coming towards you, and the center of circular motion is somewhere off here to the left, to the right on my diagram. And so I want to examine the forces that act on the car. Because I'm working quickly, I'm just going to draw the forces that I'm aware of, which is the weight, mg, directed downward. That's the force of gravity. And there is a normal force, n, directed upward on the car. The force that is the cause of the circular motion for the car is the friction force directed toward the center of circular motion. So my Newton's second law analysis of this situation is that the friction force, being the centripetal force, is equal to m, the speed squared, divided by the radius. But that friction force, F, I know is by definition mu times the normal force. And in the first moment of this, I don't know what the normal force is, but I look at my free body diagram and realize that because there's no vertical acceleration, that is no acceleration along the y-axis, that the normal force is in fact equal to the weight, and so the friction force is a very familiar mu mg. That doesn't happen all the time, but it happens often in my problem solving. I've seen it before, and so it feels right. So if the friction force is equal to mu mg, then mv squared over r is equal to mu mg. The masses cancel. Very, very common. And so what I find under these conditions is that the maximum speed that I can travel, v, is equal to, multiplying r to the other side of the equation and taking the square root of mu gr. Once again, I see that square root of gr appear. It's very common for circular motion problems. But I've got that mu out in front. The reason why is that the speed that I can travel depends on the weather conditions. Because a road that I might travel at a given speed on a particular dry, clear, warm day is different than the speed that I can travel the same curve when the road is icy, because the coefficient of friction is different. Under any conditions, if I go into a tight turn at a super high velocity, I'm apt to end up in the weeds on the outside of the curve, which is why when I drive around, I often see coming into a tight curve a sign, a yellow sign here in America that warns me that I should travel at a slower speed because of the curve. And this is the physics of that. So it's friction that makes my car go around in a curve. I'm a little disappointed in that because I know that when friction forces are exerted between the tires of my car and the road, that is what is wearing my tires out. The friction force rubs against the tires and the tire tread gets thinner and thinner and thinner until ultimately I take my car to the shop and they tell me I need a new set of tires and the tires are very expensive. That's from my point of view. From the point of view of the folks who built the road, they're a bit discouraged because when the road exerts a friction force on my tires exert an equal and opposite friction force back on the road that damages the road. And so eventually, someday, they have to go out and tear the road up and repave it, make some effort to resurface the road because of the damage that's done by the friction force. There's a way of minimizing this damage that we apply to roads that we construct, particularly when the curvature is really, really tight or the speeds are very high. For example, on highways. What we do is we bank the curve. A thing that's really obvious if you watch auto racing. Auto racing, typically driving around in an oval. The two oval ends of the track where the race cars traveling at very high speeds have to curve are banked. That is, at an angle relative to the horizontal. Let me draw a picture here in order to sort of illuminate what I mean. I'm going to draw this rather extreme. I think you look at this banked incline here and realize there's no road that you drive on in your everyday life that's banked that far. This is like racetrack banking here. But nevertheless, the roads that you drive on are banked, even if the banking angle is quite subtle. So once again, I have to try, and so here's the banking angle theta, by the way, I'll draw in here, and I have to try to draw my car coming towards you on the banked incline like this. It's tricky, it's the same car again, headlights. The car is coming toward you. This is not an inclined plane problem. I'm not interested in the car going up and down the incline. In fact, I don't want to allow it. If the car goes down the incline, you're going to end up in a ditch on the infield, and if the car goes up the incline, you're going to end up on a ditch on the outside of the road. I don't want to accelerate up or down the incline. I want to accelerate centripetally through the curve. Now, I'll begin drawing the free body diagram for this. Here I draw a box that represents the car on the incline as it's traveling towards you. Naturally, the car has weight mg directing downward. Banking the incline does not affect. You might have expected right here that I was going to break the weight down into its components perpendicular and parallel to the incline. But again, I'm not solving the incline plane problem. I'm not interested in acceleration down the incline or perpendicular to the incline. No. I'm interested in centripetal forces. Forces that seek the center of curvature and the gravity doesn't. So I like it just how it is. But because I've banked the road, the normal force is no longer straight upward, but is in fact perpendicular to the incline. As a result, the normal force has two components. It has a component that is centripetal, that is directed towards the center of circular motion. And it has a component that is vertical, which is not centripetal in any way, but is contrary to the weight. I need to figure out which component is which, sine and cosine. I want to remind you of something. That when I was doing the inclined plane free body diagram, I drew in a line perpendicular to the incline, and I was able to reason out that this angle between the weight and the line perpendicular was theta, the angle of the incline. That's why I decomposed the weight as weight cosine theta and weight sine theta. But according to some geometric rule or other that apparently is called vertical angles, this angle theta is equal to this angle theta, which means the component of the normal force that points vertically is the adjacent component, and therefore is equal to n times the cosine of theta. That is the vertical component of the normal force. The component of the normal force that points towards the center then is n times the sine of theta. I haven't included friction in my free body diagram yet, and I don't have to. When I bank the road surface, there is a component of normal force directed towards the center of circular motion, and that can act as the centripetal force. I don't need friction. By banking a curve, it makes it possible to negotiate the curve with no friction at all. So let me follow through the algebra to demonstrate that it should be so. Notice, this free body diagram, if you check back in your notes, looks identical to the free body diagram of the conical pendulum. It's the same free body diagram, with the exception that the conical pendulum free body diagram has the tension T instead of the normal force N. But it's the same free body diagram. So it has the same application of Newton's second law. It's the same algebra. And I'm going to get a familiar result. Looking at my free body diagram and realizing that there's no vertical acceleration, I can tell that n times the cosine of theta is equal to mg, the weight directed downward. And as such, the normal force is equal to mg divided by the cosine of theta. Again, my solution is proceeding exactly as it did for the conical pendulum. with just a little bit of change in notation. On my free body diagram, I see that n sine theta, the normal force, component directed radially towards the center of circular motion, so is naturally equal to mv squared divided by r. I know what the normal force is equal to. It's equal to mg divided by cosine theta, and so mv squared divided by r is going to be equal to mg divided by the cosine of theta times the sine of theta. Look, the m's cancel. And once again, I have sine over cosine. No surprise, really. The same algebra is repeating itself again. V squared divided by r is equal to g times the tangent of theta. And so I solve for the speed in this equation, and what I get is that the speed is equal to the square root of gr times the tangent of theta. But what does it mean? This is the speed that I can negotiate the banked curve without needing any friction at all. If I go faster than this speed, well, then I'm going to tend to fly to the outside, and I'm going to need some friction force down the incline to stop me. If I go slower than this speed, well, then I'm going to need some friction force up the incline to stop me from sliding to the inside. But if I travel at this special speed, no friction required at all. So think about it in reverse. If I'm building a highway, like the blue route, right here near the high school, if I'm building a highway, I can draw it on a map, and at every point on the highway, I can determine what the radius of curvature of the roadway is. I also decide what I want the speed limit on the highway to be. Using the speed and the radius, I can calculate the banking angle that I should construct the highway every meter of highway as I go. And indeed, it's been done. As you travel, since we're here in the north, traveling from the north to the south along the highway curves with a banking angle precisely calculated so that if you're traveling the speed limit, no friction is required at all. So in principle, you could get on the highway and drive the speed limit and not steer from north to south, and you would negotiate the turns under the influence of the normal force, not the friction force of your tire. In principle, your car is defective, there's wind, the road surface is not perfect, there are other cars to negotiate around, so please don't try this. But appreciate the fact that when you drive the speed limit on the highway, particularly those of you who now have a driver's license and get an opportunity to do this, when you drive down a highway at the speed limit, you really just have to tweak the steering wheel. Nudge it a little bit this way, a little bit that way, just to keep yourself on course, to correct for those errors. Otherwise, the car negotiates the curves of the highway under the influence of the component of the normal force that is the centripetal force in this problem.